Hello, everyone, and welcome to the new normal. Today what we're going to be focusing on is taking the ideas that we learned from the variational principle and using them to actually develop a way to determine the energies of the molecular orbitals. So we're going to be focusing on a system that is looking at a relatively simple case of just going to be combining two orbitals, which should end up producing two molecular orbitals. So we're going to start by looking at a trial wave function, psi, which is going to be composed of two atomic orbitals, psi A, psi B. So one could think of this as the classic form of I'm mixing two s orbitals on, say, neighboring atoms, say hydrogen or carbon. It could be an H and a P. Doesn't really matter at this point. By convention, we're just going to be looking at one atomic orbital on A, one atomic orbital on B, combine them together, we get a new molecular orbital. So when we're going to be doing this, this should give us a classic equational form of my new MO is going to be combined as some linear combination or superposition of the states psi A and psi B with probabilities CA squared and CB squared, or at least proportional to those, because we are still dealing with an unnormalized function. So be aware of that. But you can at least quickly get the ratios of the two states by taking the squares of the coefficients. So it is worth noting that if I'm going to be looking at, again, as we have previously, a homonuclear compound, these are likely going to be the same orbitals. So they're both, say, would be PZ orbitals. And then by definition, because the orbitals are identical, so will the coefficients. But we'll go ahead and show that a little bit later as we continue to develop this form. So I'm concerned about the energy of this brand new wave function. How do we get the energy? Let's go to our good old friend, the Schrodinger equation. So we can essentially generate this through an expectation of states. This form is actually through an expectation value. It is worth noting that this form does assume that energy is an eigenfunction, but we can go ahead and do that for now, because the general idea is that even if it isn't, this should be a normalized wave function. We still get one on the outside, even if we don't have an eigenfunction of the Hamiltonian. So this equation should be fairly universal. No real major assumptions here, besides the fact that I'm using a normalized wave function. Now, if I do this, well, what I can then do is go ahead and rearrange my equation to pull the energy term out in front. And so if I do this, then I just have the energy as a ratio of two integrals. So what we're going to be trying to do is analyze each of these integral components separately, both the numerator and the denominator. And it's worth noting that the denominator isn't anything too unusual. We've played with this form a lot so far the last couple lectures. So denominator can simply be given as the integral of the square of the wave function, which then just lets me insert my wave function in terms of my atomic orbitals. And so then I just get a polynomial term. Watch out, because now it's squared, which means have fun foiling it out. In truth, though, this one isn't too bad. We end up with having three components, because again, as I distribute through the FOIL, I can then integrate each of the resulting sums. So we'll have an integral of an expression just in terms of A, an integral just in terms of the B atomic orbitals, and then we have the mixed orbital case. Well, we've played with this form before, so you might be able to spot what we're going to be doing next. First, we're going to be distributing the square, pulling out all of the coefficients. So for example, I now have the essentially the probability of finding A times the integral of the square of the wave function of the atomic orbital A. And same thing with B. Now, this last term is kind of the tricky one, as I'm pulling out twice the mixed coefficients. So the probability, the square root of the probability of A times the square root of the probability of B times our good old friend, the overlap integral. So our last integral drops the overlap integral. Classic symbol, we love this guy. And because I'm dealing with normalized atomic orbitals, because all atomic orbitals should be normalized, wave function, the atomic orbital of A, its integral over all space, 1. Same thing with B. So what we did is we took this big integral and we broke it down to simply the sum of the probability of finding the wave function in state A plus the probability of finding the wave function in state B times more or less the probability of finding it in that overlap region. So that brings us back to the numerator. So now we have to go ahead and play with this guy. And when we do, we can more or less play the same trick we did before. We can insert the polynomial expression for each of our atomic orbitals. That go ahead and insert that into our wave function. And now this guy is a bit of a mess because it means that I'm applying my Hamiltonian operator to each of these wave functions. And then I'm applying the wave function of A times each of those resulting possibilities plus the wave function of B times each of those resulting possibilities. And then I have to integrate each of those. And when you do this, it generates a possible of 4 states. And again, we went ahead and pulled out the coefficients because we'll end up with squared coefficients. The easy case is it's going to be the square of the of each coefficient. And then we get these 2 mixed states that are a bit more annoying, where we've got the CA times CB and then CB times CA. Now, this guy should more or less be describing the energy of A and the energy of B. We'll deal with that later. But these mixed states, it's worth noting that the only difference in between these two is the order in which we're applying the operators. Because I'm still having a mix of atomic orbital A and B, and it's just whether the Hamiltonian is being applied to A or B. Now, this is where we get to go ahead and pull up some of our old quantum mechanical identities. The one we're specifically going to be using is, since the Hamiltonian is a quantum operator, that means it's Hermitian. And more or less, the order in which we apply the operators is going to be equal because our wave functions are real and we've gotten rid of all those nasty imaginary numbers. And by doing so, we don't have to worry about our complex conjugates. So thus, the act of applying the order in which we're applying the Hamiltonian to A or B doesn't matter as long as the 2 functions are symmetric. So B and A and B. This wouldn't work if it's B and A and C or anything like that. But as long as the 2 functions are identical, the order in which I apply them doesn't matter. Gotta love Hermitian operators. And the beauty about that is that it lets us combine these 2 last terms. So now I took an expression that was in terms of a nice, beautiful 4 different integrals, and I dropped it down to 2, or down to 3. So now I only have to worry about 3 integrals. But it's still worth noting that this is a messy form, and we're going to spend a lot of time over the next couple lectures dealing with how we manage this. And just to make it more convenient, so I don't have to list out the full integral forms each time, we're going to abbreviate each of these integrals as a simple variable. So whenever you see these variables, remember, I'm talking about a full integral form. So let's go ahead and walk through them one by one. The first one that we go ahead and start with is applying the Hamiltonian to the operator A. So you may know this guy as the expectation value of the energy of A, because applying a Hamiltonian to a wave function is indeed just an expectation value. So because I'm applying it to orbital A, even if it isn't an eigenfunction, I'll still return back the energy of A. So this is the energy of my atomic orbital, okay? But because there's a little bit of nuance to how we work with the system, we're generally going to describe it as alpha A and refer to it as a Coulomb integral of A. So this can, in a large part, be thought of as the orbital energy of A. And as such, it will have units of energy. Now we can do the exact same process for B. And it gets a little bit more messy when I'm going with this mixed state, because that isn't an expectation value. It's kind of describing the energy of a mixed system. So we're going to describe this as a resonance integral. And again, because of the act of the Hamiltonian being Hermitian, it doesn't matter which order we're applying the Hamiltonian. So this will be a symmetric form. And we're going to describe it with beta. And so the resonance integral, one of the ways you can think about it is it's going to be the energy of the electrons in that intermediate space. And as such, this is often stabilizing because the electrons will much rather be somewhere near a nuclei than off on their own. So we're typically looking at a negative energy value when we're talking about resonance integrals. Now, one of the nice parts is that now I can replace these big integrals with these simple terms. And especially when we're thinking about the physical meaning, we can actually get something out of this much smaller expression. So when I'm looking at, again, applying the Hamiltonian to my molecular orbital wave function, we can more or less think of this as an energy and treat it as the probability of the function being found in A times the energy of atomic orbital A, times the probability of the wave function being found in B, times the wave energy of orbital B, plus the probability of the wave function being in this intermediate overlap region times the energy of that overlap region. And that's really what we've kind of embedded in this form. So if you're looking for kind of a logical hook or a handhold when thinking about this system, that's a good place to start. So as a reminder, we did all of this to get to the energy of our total orbital. And we had two forms. We had two integrals. So let's go ahead and insert our functions back into the integrals. So what we're really finding here is we can now think of this top expression as more or less being the energy of the system. But because we're mixing two orbitals and we don't necessarily have a normalization factor, that's more or less what this bottom function is acting. It's acting as my normalization value. So this gives us our true energy of the system by adding up the energy of each component times its relative probabilities times essentially converting those relative probabilities to a normalized notation. And that's more or less going to be the expression for the electronic energy. Now, here's the trick. I need to try and figure out a way to determine the true energy of my system. And this is where the variational principle comes in. Because while this will give me the energy of any given arrangement, so I can say if I'm looking at any combination of my two orbitals, I can just throw in the various probabilities of being found in each state, and I'll get back the energy for this configuration. So if I know my basic energies, I can just keep trying configurations. But this will take forever. So if I want to determine the true energy of my system, where the approach I'm going to want to do is using the variational principle and saying, well, let's look at how many variables I have to move. So S is really going to depend on the overlap of the system. That's going to be mostly determined by geometries. Same thing with beta. The alphas are intrinsic to the orbitals themselves. So the only things that I can move are going to be, or my only variables are going to be the coefficient of A and the coefficient of B. So variational principle says, well, the energy is going to be at a minimum if I move A and anywhere else goes up. So if I'm trying to find a minima with respect to the coefficient of A, we use our classic calculus trick, take the first derivative, set it to 0. And that's exactly what we do. Now, because this is a really messy derivative, we're going to kind of skip over it and work with the rearranged form. So when we do this, we can get the derivative with respect to the coefficient of A into this, I'll be honest, kind of long form, but you'll notice it's going to depend on the actual energy of the system and the coefficients of A and B. And again, our normalization function manages to limp along with. And turns out we can do the same thing for B. So we know that we should have a global overall minimum in the energy when both of these two things are true. So what we can try and do is set both of these functions to 0. Now, unfortunately, I've got 3 variables, but it is worth noting I can simplify the heck out of these two equations, because since the right side of both of these equations is 0, I don't need this whole function to worry about how I get this whole function equal to 0, because this guy won't matter, because all I need to get is the numerator equal to 0, and then the whole function's equal to 0. Denominator doesn't matter. So I can drop it out on both functions, and then 2 times 0 is still 0, so I can drop that factor of 2. So all I need to worry about is how I can choose CA, CB, and E such that I can get this inner term equal to 0. And these are called the secular equations. And it's more or less just looking at those inner factors. And while in this case, I did it for a mixing of 2 orbitals, you can scale this up to 3, 4, or 5. And I'll show you a little bit more of the general procedure of doing that later. But for now, what I've done is I've taken all of those big equations that I started with and simplified them down to the essential bits. Now, I have a system of equations. So we can try and do this the old algebra way, insert into each other, try and simplify the terms. You can get this whole expression down just to E by inserting A's and CA's into CB's and so forth. But it turns out there's an easier way. If you have a series of equations that you're trying to solve, set it up as a matrix. So we can express our secular equations in a matrix form, and this is going to be quite useful. So a way to be thinking about how you set up a series of equations in terms of a matrix form is what it essentially is telling me is that CA times the first term plus CB times the second term gives me this top value. And CA times the first term plus CB times the second term gives me the second value. So we can essentially just treat it as this row times this column gives me the value in the first row. This row times this column gives me the value in the second. That's more or less how matrices work. Is there a condensed way of writing a lot of linear equations all together? So this is actually a quite useful form. And if you want to verify, doing this process should give you these 2 equations back. But it turns out that by using this matrix form, we can use a set of well-established rules. If I have a matrix times a vector and I get a 0 vector back, it turns out that this is only going to be true if I set the determinant, remember our good old friend determinants, of the matrix equal to 0. So that means that I can figure out exactly what energy will give me a 0 value. Because here's the beautiful part. By doing this, we eliminated the influence of my 2 coefficients. So now all I have to figure out is what energy satisfies this determinant. And that's going to be the energy of my molecular orbital. And that's the power of the secular equations. Now, again, taking this matrix form, if you are more comfortable with linear algebra, we can actually, for a 2x2 determinant, do this pretty quickly. Gets a little bit longer if we move to 3x3s, and at that point, you're probably going to need a matrix solver like the one available in Mathematica. So again, as a review of matrices, they work by taking the first and fourth element, multiplying them by each other, and then subtracting them by the product of the second and third element. So essentially, it's a little bit like cross multiplication in a sense, but it's really what we're doing. Diagonal minus diagonal. And so we can write this out as our two diagonal terms times each other minus our two diagonal terms times each other. And there we go. So now I just need to solve this little bit simpler form. Unfortunately, that means I need to FOIL this out and FOIL this guy out because yay squared terms. Now this process can take a bit, but I went ahead and worked a little bit ahead and collected all of these various FOILed out terms in terms of the energy. And when you do this, we're going to have an energy squared term, the one value coming from this first group, and the one involving the s squared coming from this expression. So when we do that, we're going to have an energy squared term, an energy term, and a value that has no dependence upon energy. So if you want some practice, feel free to give this guy a try. But you'll notice that this is a bit longer of a form. And this guy looks like fun to solve. But you may, if you're really observant and you haven't quite tuned out after 20 minutes of listening to me ramble on, what you may notice is this is a quadratic equation because this whole thing is set equal to 0. And I have my variable energy squared to the first power and to the 0th power. This is the classic form of the quadratic equation. Now watch out because our A, B's, and C's are a bit nightmarish. Here's my A, here's my B, and here's my C. All right, so we can take this, chuck it into the quadratic equation, and we get a very long expression. But what's worth noting is that this long expression is going to give us all possible energy values that give us a minima. So again, we got this by setting our first derivative equal to 0. We found two minima, which should hopefully make sense because if I mix two atomic orbitals, how many molecular orbitals will I get? I'll get two orbitals back. And each of those orbitals will have its own energy. We found the energy of each of our molecular orbitals when I mix two atomic orbitals. This is hugely powerful. And it's worth noting that we now have an exact expression for the form. We're going to spend a lot more time applying this next time because let's be honest, this is a big equation. And in order to really make it sink in, we're probably going to need to make a series of approximations to simplify it down a little bit. But I want to point out a couple of the key features. So first, you can imagine by setting S equal to 0, so just the overlap out of convenience, setting the overlap equal to 0 just to illustrate a point, that would bring this second term down to 2. And what it would make is that my energy is going to be centered around the average of my two atomic orbitals. Now, this will be shifted a little bit depending on the extent of overlap. But the energy is going to be centered around the average of my two atomic orbitals plus or minus some expression that depends upon how the extent of overlap between my two orbitals, because that can push them either further or closer apart, and the actual energies of my two atomic orbitals. So we'll be talking a little bit more about that later. But this does make a certain amount of sense. That I'd expect when I'm mixing two atomic orbitals that one goes up, one goes down. And the energies tend to be centered around the average of my two atomic orbitals. So this this helps support what we've been intuiting so far. Next time, we're going to try and apply this to some specific systems. Till then, take care, stay healthy.